So now I want to tell you about the philosophy of statistics, possibly the two words you hope never to hear in the same phrase, philosophy and statistics. But actually it's quite interesting, which is something I hope to show you today. And also I want to disabuse you of the idea that statistics is something set in stone, that there's some cookbook routines, and if you just memorize these arbitrary routines and press the right buttons, you get the right answers, and that's all there is to statistics. In fact, there's passionate debates at the heart of how you do statistics, and what you've been taught is one way of doing things that happened to win the day about 100 years ago, a bit less. But the alternative way, Bayesian statistics, is now making a comeback. In fact, in terms of papers published within statistics, more of them are Bayesian than non-Bayesian. You can solve more problems with Bayesian statistics than orthodox, conventional statistics. And indeed, there are deep problems with significance testing that I now want to tell you about and alert you to and offer you a solution. Now, these points are important because even if you don't get involved in research, you're all consumers of research. In that, newspapers, for example, will report on recent findings, and they might tell you, for example, you have a sore back. Well, there was no evidence that chiropractic helped you fix your back. They might say things like this. Now, you have to be able to evaluate, so do those claims, what grounds do those claims have? And I want to argue that a lot of those claims that you hear where something is not effective are groundless. But unless you understand at least some of the concepts involved, you won't be able to evaluate that evidence and therefore make decisions for yourself about what you do. Roughly speaking, there's two ways of making a complete system of statistics. And they both became formalized in systematic ways around the 1930s. On the one hand, what we have now is based on a way of thinking, a system of thinking, put forward by Neyman and Pearson. Although probably you don't know those names because you just taught statistics. But what you're taught is meant to be following the principles laid down by Neyman and Pearson, which give a systematic way of understanding what you're doing in statistics. And really, whether you go that Neyman and Pearson way or you go the Bayesian way, it starts with a question that sounds a little bit conceptual or maybe just academic, and that is, what is probability? So to get us going, what I'd like you to do is use probable, or probably, or likely, some word like that, in a sentence with the person next to you, and then think about what does the word mean. So let me just give you 2 minutes to say something is probably true, or probably something or other. So just make up your own sentence, and then think about what does the concept probable mean in that context. Go. Okay, well, there was two directions, roughly speaking, you could have gone in defining probability and in the examples you gave. One you can call the objective and the other subjective. So the subjective definition means how strongly do you believe something. So if you say something's probably true, that means you have some conviction in it. So that's the subjective definition because it's about how strongly you believe something subjective. The objective definition is about a property in the world, namely the relative frequency with which something happens. So it's something you discover about the world. So if you say, what's the probability of the coin coming up heads? Well, you could flip the coin many, many, many times and look at the proportion of times you got heads. And then that proportion in the long run, if it's 50% heads, you say the probability of heads is 50%, or 0.5. So it's a long run relative frequency, which is an objective property of the world. Now, for there to be a long run relative frequency, you need to be able to repeat the event lots and lots and lots of times. So you need what's called a collective of events. You need the set of all the events that you're repeating. Now, if you said it will probably rain tomorrow, there's not a set of events, there's just tomorrow. And either it rains or it doesn't rain. So there's no relative frequency. You're either wrong or you're right. But you can have a strength of belief in whether it will rain tomorrow. So that example would be a subjective probability. It's how strongly you believe something. If you said the probability of a British person having black hair, something, well, that could be a relative frequency. You could count the number of black-haired people in Britain and divide by the number of people. That's a relative frequency. That's something objective you can discover. But if you said, what's the probability of the next British person I see having black hair? That's just a strength of belief matter, because the next person you see is just one person. It's a one-off event. So just put your hands up if you understand the difference between subjective and objective probability. Does that make sense to you? Excellent. So now just tell the person next to you, was the example you used, was that a subjective probability or an objective probability? Okay, so now if you talked about how likely a theory is of being true, that's a subjective probability. Because there is no long-run relative frequency. The theory is just true or false, that's all there is to it. So if you have a theory like this cancer drug is more effective than placebo, you can only give a subjective probability to that. It's just true or false. But you can believe in it with different degrees of conviction. So if you are interested in statistics telling you how probable, say, a null hypothesis was, or something like that, you'd have to start with the notion of a subjective probability. Neyman and Pearson said, we should start with the notion of an objective probability because, well, it's more objective. And we're in the business of doing science, and science should be, well, objective. So, let's use objective probabilities and see what we can do. Well, one thing we can't do is to say how probable is a null hypothesis. That's just ruled out from the beginning. And we'll see in examples why that's ruled out. We have to be talking about some sort of relative frequency. So we could have a hypothesis like this drug is just a placebo cure for depression. so we are interested in theories. We can't talk about the probability of that theory, but we could say, well, given that theory is true, how probable is it that we get some data? For example, we could run an experiment where we give people either a placebo or the drug. We get them to rate how happy they feel, and we look in the difference in happiness between the drug and the placebo. And you can do a t-test on it, and we could work out the probability, assuming there's no difference, really, so assuming the null hypothesis, the probability of getting a t-value of, say, 2 or more. Now that's that's something repeatable. We can assume the null hypothesis is true, collect some data. Assume the null hypothesis is true, collect some data, collect some data, collect some data. In principle, we could imagine repeating that indefinitely, and we could look at the proportion of times, say, we get a t-value, or data more extreme than a certain amount. So the collective we're using here, the sort of the set of events, could be something like measuring the happiness of each of 50 people in drug and placebo conditions, given the drug operates just as a placebo. So that is a probability we can calculate. Now, a little bit of terminology here. We can talk about the probability of the data given, that's this vertical line, the hypothesis. But that's different from the probability of the hypothesis given the data. I know that sounds kind of arbitrary at the moment, but I'll be making that point clear. We can't talk about the probability of the hypothesis, or the hypothesis given the data, because it doesn't have an objective probability. Probability of the hypothesis given the data is what you call the inverse of the probability of the data given the hypothesis. Now you say probability of H given D, probability of D given H, it all sounds the same to me. So let me give you an example where it won't sound the same. Let's say I looked at all people who had their head bitten clean off by a shark. And I tried to discover the proportion of them that were dead. Now, that proportion would be 1. So the probability of dying within 2 years, given your head was bitten clean off by a shark, is 1. Well, now let's invert that, and I take all the people who died in the last 2 years. So I go to the morgue, I look at the causes of death, I scour the seabed for headless corpses, and I find of all the people who died in the last 2 years, the proportion of them that died from shark bite to the head. And that's probably pretty much 0. It might have been the odd one, but it's as close to 0 as you can get. So you see here, the probability of dying given head bitten off by shark is 1, but probability of head bitten off given you're dead is fairly close to 0. And that's as different as 2 probabilities can get. So if you often start thinking, well, why should I think probability of H given D is any different from probability of D given H, just think about sharks and heads, and hopefully that makes it clear. So just put your hands up if you understand that the inverse probabilities are different things. They can be radically different, very different. That's great, good. So statistics can't tell us how much to believe a certain hypothesis on the conventional approach. All we can do is set up decision rules for accepting and rejecting hypotheses, which will have long-term error rates. So we can work out the proportion of time would be wrong in making the decision procedure. For example, we could have a decision procedure that goes, I'll calculate a t-test, and if my t is greater than 2, I'll reject the null hypothesis. You can decide that's going to have a certain error rate, say 5%. And then you use that decision rule, keeping the error rate at 5%. Now, the reason why I say 5% is because 5% is a number you know. It's what you know is the significance level at which you're making tests. When you're making a test at a 5% significance level, that means you're controlling your error in saying there is a difference when the null hypothesis is really true at 5%. But that doesn't tell you how much you should believe in the null hypothesis. P-value you get does not tell you how much you should believe in the null hypothesis. It doesn't tell you how probable it is. Let me make that clear. Let's say you have a coin. It might be a completely fair coin, or it might be I've magnetized this tabletop here, and the coin is actually a bit of a magnet. So when I throw it, it could be biased to come down heads at a different rate than 50%. So this is how significance testing works. Let's say I toss it 6 times and I get 6 heads. Well, I can work out the probability of an event this extreme. It's 0.03. It's less than 5%. So we say it's significant. That's a decision rule in which I'll make the wrong decision 5% of the time, given the null hypothesis is true. But we can control that error rate or whatever you specify. We've happened to settle with 5% because Fisher used 5%. And we just use this little rule. If we get p less than 0.05, we reject the null hypothesis. That's what you've all been taught to do. Now, if I toss that coin 6 times and I got 4 heads, an event as extreme as that or more extreme is pretty likely. So you don't reject the null hypothesis. So it's non-significant. So that's what you've been taught, right? So now consider this. This time I throw the coin only twice. I get 2 heads, which is as extreme as I could possibly get with only 2 throws. That's the most extreme I could get. Would you reject the hypothesis that the coin is fair? Would you accept it? Or what would you do, given those data? I might have a biased coin, I might have a fair coin, I flip it twice. What decision, if any, would you make on the basis of those 2 coin flips? Just tell the person next to you, what would you decide based on those data, if anything? Okay, so I can tell you, by the way, that the p-value for this is 0.5, not 0.05, 0.5. So non-significant. Do you accept the null hypothesis? Do you say, great, the coin is fair, let's gamble? Or do you say, well, I know it's non-significant, but you cannot reject the hypothesis of fair coin, but actually the number of trials is too low to tell me anything. You just say, there's not enough data here. I can't tell there's almost anything from that. Okay, you can rule out the hypothesis the coin only lands tails, but the coin could be biased to all sorts of extent, and you just can't tell. Do you think the probability of the null hypothesis is 50%? Right. There's no reason at all to think the probability of the null hypothesis is 50%. In fact, You might have had a look at the coin and you saw it had heads on both sides. You knew this coin was utterly biased. Of course it produces two heads in a row. It was a biased coin with two heads. P-value is 0.5. Is the probability of the null hypothesis, the probability of it being a fair coin, is that 0.5? No. You know 100% it's not a fair coin. The p-value does not tell you the probability of the null hypothesis. This 0.5 is just telling you, in this particular case, your data is insensitive. It cannot distinguish between a fair coin and the alternative hypothesis that there's bias. P-value does not tell you the probability of the null hypothesis. It does not tell you how strongly to believe in the null hypothesis. A non-significant result, to summarize the conclusions from that, could be because actually there is evidence for the coin being fair, or because there's not enough data to say anything at all. There just isn't evidence. Significance testing does not distinguish between those two possibilities. In fact, Ronald Fisher, one of the great founders of modern-day statistics, said, if you get a non-significant result, suspend judgment. Study finds a non-significant effect of meditation on level of anxiety. That's all you're told. This could be a newspaper article you read. What do you conclude? Well, you can conclude essentially nothing. How do you know that that non-significant effect isn't actually like just throwing a coin only twice? It might be that they did not have enough data to draw a sensitive conclusion. You do not know that if all someone tells you is there was a non-significant result. I read a book on alternative medicine, talking about chiropractic, traditional Chinese medicine and so on, and it just said it was non-significant, non-significant, non-significant. Came to the end of the whole book and I'd learned nothing. Because all it said was, this study was non-significant, that study was non-significant. There's one message I want you to take home from this is a non-significant result by itself means absolutely nothing. Here's a screen grab I took of running some software on the website of Jeff Cumming, Melbourne psychologist, where he simulates the same experiment over and over and over again. So this just keeps running. It's exactly the same experiment where there really is a difference in the population. It's set up to be at the typical level of sensitivity of psychology experiments. Technically, we call it a power of 50%. And these are the p-values that he gets. Don't worry about this side, I just want you to look at the p-values. So for the first experiment, the p of 0.23, non-significant. If we go on, well, here's a p of 0.024, significant. So his point, he calls it the dance of the p-values. Even when there really is an effect there in the population and dealing with the typical levels of sensitivity of psychology experiments, p-values will dance all over the place. So look here, there's a p-value of 0.034. You would say, great, my experiment worked. There really is a difference there. You would be ecstatic. So you say, well, I better just run this again to make sure, and you get a p of 0.74. You would be depressed. So what the hell has happened? And you might think about, well, did we run it in the afternoons more? Is it the time of the, is it different time in the term? Were there different experimenters involved? You try and come up with all these reasons. You don't need a reason. P-values just jump all over the place, even with no reason. Because in this case, these are mathematical simulations. These are identical simulations each time. There is no time of day effect in here. This is just how p-values behave. So here's some quotes from statisticians. The continued very extensive use of significance tests is alarming. After 4 decades of severe criticism, the ritual of null hypothesis significance testing, mechanical dichotomous decisions around a sacred 0.05 criterion still persists. It does not tell us what we want to know, and out of desperation, we nevertheless believe that it does. Statistical significance retards growth. It never makes a positive contribution. I mean, I have selected particularly extreme quotes here. Not everyone agrees that it's as bad as this, but I want you to see that it's not accepted consensually either. So what's the other way you could go? Well, you could start from the notion of subjective probability, your personal conviction in an opinion. Now, what you begin with is just up to you. That's why it's subjective. But you have to revise that probability when data comes in, other information comes in ways consistent with the axioms of probability. That's what statistics based on subjective probability asks you to do. How strongly you believe in the theory to begin with, well, that's up to you. But having made a commitment to that and to, say, certain assumptions like the data are normally distributed and so on, you then have to revise your opinion in certain ways. This is a notion of probability that applies to the truth of theories. So you can talk about the probability of hypotheses or how much you should change your opinion in a hypothesis. In fact, if you just rearrange the axioms of probability in a few short steps, you come up with exactly how you should change your opinion given some data, and that's called the Bayes factor. It's how much you should change your strength of opinion in the alternative hypothesis versus the null. How much you should change your opinion is, I think, in other words, the strength of evidence. Because evidence is what changes or should change your opinion in something. So the Bayes factor is a measure of strength of evidence derived from first principles. In other words, derived from the axioms of probability. Now, often what we would like when we collect an experiment, we set up a null hypothesis and say there's no difference. We say we have a theory that says there's some sort of difference. And at the end of collecting data, it would be nice to say, did we have evidence for the null, no difference, evidence for there being a difference, or really not much evidence to speak of. We'd like to be able to make that three-way distinction. Now, when you use p-values, they do indicate in some rough way something about evidence, but to the extent that they do that, they only make a two-way distinction between this and what's in this box. So no matter what the p-value, no distinction is made between these two things in the box here. In other words, you can't say, because my p-value was 0.8, therefore the null is supported. You often see this in papers. People say, the p-value is 0.7 or something, therefore this must be good evidence for the null hypothesis. No, it doesn't mean that at all. It could just be you had a big standard error, there was a lot of noise there. You really have no evidence to speak of. That's why you got your big p-value. Just looking at the p-value, you cannot tell that. Now, the Bayes factor is a continuous measure of evidence where 1 means both theories or hypotheses are equally well supported. And the way I've coded my Bayes factor calculator, which you can get on the web, more than 1 means more and more evidence for the alternative versus the null, and less than 1 means more and more evidence for the null versus the alternative. Jeffreys, who developed the system of Bayes factors in his book in 1939, so essentially the same time that Fisher and Neyman Pearson were developing their versions of statistics, he introduced a convention and said a Bayes factor more than 3 you should take to be good enough evidence to start taking notice of. He called it substantial evidence. And indeed, he said the reason why he chose this is the problems he worked on, when Fisher gets something significant at the 5% level, he tends to get a B greater than 3. And indeed, that's what I found. When your effect size is about what you expected, the Bayes factor of 3 matches up with a significance of 5%. That means by symmetry we have a criterion for evidence for the null hypothesis. And that is, if the Bayes factor is less than a third, you actually have substantial evidence for the null hypothesis. The Bayes factors make the three-way distinction that we wanted to make and you couldn't before. If you have a Bayes factor more than 3, you have evidence for the sort of difference your theory was talking about. If you have a Bayes factor less than a third, you have evidence for the null hypothesis. If you have a Bayes factor around 1 within those limits, you have no evidence to speak of. Now, the fact that we hadn't been able to make that three-way distinction before is not news. As I say, it was pointed out by Fisher right from the beginning. So psychologists and any user of statistical inference have felt a bit funny about non-significant results. They sort of recognize them not quite evidential. So what happens when you run a study and it's non-significant? It's tended to be buried. This is what Robert Rosenthal called the file drawer problem. You have all these studies that were non-significant that are filed away and not published. Well, then you end up with a biased publication record. So if you have a bunch of people looking at a phenomenon that's interesting, the people who get significant results publish, those who get non-significant results bury them, and they could look like there's an effect there when there's nothing going on at all. But the converse problem is even worse, I think. And that is, you see all the time in every talk I go to and practically every paper I read, people using non-significance to assert the null hypothesis. So to demonstrate this, I just picked up a prestigious journal, Experimental Psychology Journal, and just flipped through all the articles and found in almost every case, non-significance was used to assert no difference. And it seems to work like this. When a key result is significant, feel free to publish it, and also feel free to interpret any other non-significant result in the paper as evidence for the null hypothesis. In other words, if your key result is non-significant, treat it as non-evidential and bury it. But if the key result is significant, then treat non-significance as evidential. It's a completely irrational manner of treating non-significant results. Furthermore, it's a method that leads to dire consequences, not just because our theory development is based on utterly groundless procedures, but it can be life and death. For example, when a drug company asserted that its drug did not produce more suicides because the rate of suicide increase was non-significant. In fact, when more data was in, it was showing it did increase the suicide rates. Non-significance by itself does not mean no effect. This is very common. The main effect of manipulation is significant, but when the interaction with something like gender is non-significant, the authors feel utterly free to say, but this did not depend on gender. Almost every paper or every talk I go to, this happens. But no inferential conclusions follows from a non-significant result in itself. So this is something to bear in mind for your projects and dissertations. Also, to bear in mind whenever you read the research literature, because it is hopelessly confused in almost every paper you read on this issue. It probably draws illegitimate conclusions that you will have to correct and judge for yourself. And this has led to what's called the replicability crisis. It was part of the reason for the replicability crisis, credibility crisis, in psychology and other disciplines. Because if there's a sense you can only publish if you get a significant result, and let's say you can analyze the experiment in a number of different ways. Do you put in gender as a factor? Do we exclude outliers by this criterion or that criterion? Do we transform the data to make it a bit more normal this way or a bit more normal that way? You have possibilities, analytic flexibility. One of them might just tilt your result in the direction of significance. And indeed, we see the evidence for this in this paper about a peculiar prevalence of p-values just below 0.05. They had a look at the significance values in some prestigious journals, and it should be a smooth curve, but look at this. Just below 0.05, there's this unseemly little bump just here, which indicates people were trying out different ways of analysing the data until it just went below 0.05. Now I can publish. And I just want to bring up one final issue before we finish. See, Bayes factors are different because they can indicate evidence in either direction. They can indicate evidence for the null as well as against the null. You don't have to push in one direction. It doesn't completely solve the problem of analytic flexibility, but at least you can draw conclusions either way. which should relieve bias in the publication record. You can publish papers claiming no effect on just as good an evidential basis as those claiming an effect. Now, there's another example of poor practice that comes about and is invited or even demanded by significance testing that Bayes solves. Standardly, with significance testing, what you have to do is you have to specify the conditions under which you would stop running subjects and then stick with that decision. So if you say, I'm going to run 30 subjects, you run 30 subjects, you test the significance, that's it. That is the significance. You can't do anything more after that, like run more subjects. So what do you do when you get a P of 0.08 after running your 30 subjects? It's not quite significant. So you say, let's run 10 more subjects. You just violated your stopping rule. You're not allowed to do that with significance testing, because if you do that often enough, you're actually guaranteed to get a significant result, even if the null hypothesis is true. But the reason why you thought you could do that probably is surely getting more data is getting more evidence. And the evidence isn't quite conclusive yet, so let's get more evidence. Well, you're right to think that, but if you're going to do that, you need an actual measure of evidence. P-value is a funny half measure of evidence. Bayes factor is a measure of evidence, and that's why with a Bayes factor you can get more evidence and then evaluate the evidence. So with a Bayes factor, you can collect more data when you think you need more evidence. That's perfectly legitimate. So it solves that particular problem. So it takes you out of a sort of moral paradox that you have with significance testing. If after P equals 0.07, if you run more subjects, get P less than 0.05 and report it significant, you have cheated. All right? So let's say you don't run more subjects. You can't publish it, you bin it, you've wasted taxpayers' money or charity money. In any case, you've wasted your time. And in any case, importantly, you've wasted data that's relevant to answering a question of interest, and that's immoral. So you are morally damned whatever you do. Bayes allows you to step outside the circle of moral damnation. So, at the end of the day, actually, you have a choice between two ways of thinking about what you're doing. You could be trying to control the proportion of errors you make in the long run. That's conventional statistics. Or you could be trying to measure the amount of evidence you have for and against a certain hypothesis. Now, you might think you kind of like both. But you have to make a choice about the thing that you really want. Now, I'd suggest, if you think about it enough, what you're really looking for is evidence and knowing how much should you change your opinion about one hypothesis versus another. And when you do get sufficient evidence, that does constrain error rates. It's not as these things are completely independent, but if you rigidly try and control error rates, you fall into all the sorts of problems that I've been talking about. Anyway, I just wanted to let you know that there are these debates, so at least if you don't take this matter any further, you know the statistics you've learned is just one way of doing things. There are other ways. Furthermore, things are changing. When I first started lecturing this here, 2005, I said 10 years' time, results sections will look very different. I was kind of 10 years out, because it is 10 years' time now. But what I see is more and more Bayes factors appearing in results sections. And editors now tell people when they draw conclusions from non-significant results, they say, do a Bayes factor there, because people constantly email me and say, how do I do a Bayes factor? So now it's sort of going like this. I can see the tide changing. The APS, Association of Psychological Science, says any journal of theirs will accept results sections that are purely Bayesian now, and no editor can say otherwise on that matter. Bayes is taking off. So now I'm predicting in 10 years' time, things will look radically different when you look at results sections of journals. Thanks very much.